There we
There
go.
it is. We can see it.
Yay! Okay, good. Let me get things adjusted on my end. There we go. All right, well, let's get started. Oh, and I've always been told to say this. Unless you have a question, mute yourself because otherwise we hear all these HT squawkings and spouses and dogs, all that stuff. So mute yourself. And I love to be very interactive, so I encourage you to ask questions, and I'll go real time. Happy to do that. By the way, I should ask, how long am I allowed to go tonight? I know it's 7 o'clock your time. How long? When is my dead stop?
As long as you want. Oh, sorry.
I usually go, with questions, it usually goes up to 90 minutes, depending on how many questions. Is that okay?
Yes.
Yeah.
Yes.
Yes. Okay. Good. All right. So by all means, interrupt me if you have questions. Let me get started. Okay. Let me go to the first slide. There's my little fake laser pointer. Yeah, it's working. All right. So the name is Greg Mihran, like mirror, mirror on the wall, but everyone pronounces it wrong, so don't worry about it. I was born back east, up in upstate New York. Got my electrical engineering degree in Cleveland, the mistake on the lake. Came out to California to work for Hewlett Packard and been here ever since. Worked at HP, Cisco, a bunch of startups. Had a lot of fun. Just retired a couple of years ago. I had to force myself to retire because I was having so much fun. But I'm glad I did because then I got more into portable antennas and PODA, which is why I'm here. We have 5 grown kids spread around the country, 6 grandkids. I'm a bogey golfer. I love golf, but the best I could do is bogey, and that makes me happy. So that's good. I love hiking. I'll be doing my first QRP activation tomorrow. I'm going to hike up a 1,200 foot peak to do that. With these band conditions, I doubt I'll get many contacts, but it's going to be a lot of great exercise. I do a lot of music, performing, and recording. But my geeky passion, and I am a geek, happy to be called a geek, is Parks on the Air. I started back officially in February of 2021 as the cycle was kind of ramping up. So glad I did. I should be making my 1,000th activation this year, which is ludicrous. 1,000 POTA activations is nuts, but I'm a sideband guy. I love to talk. Got over 80,000 QSOs, and I'm an ICOM guy, so I do a lot of ICOM stuff. So, and I'm located now. You're talking to Silicon Valley, right up here. I heard about the barbecue place in San Diego. That's way down here. That would be a long, long trip for some great barbecue, but I'll keep that in mind because we do have a daughter down there in San Diego. All right, let's keep going. You can take notes if you want, but you don't have to because one, this is being recorded, so you can play it over 1,000 times. But also, all of my antenna designs are PDF files. They're all 15 to 20 pages long, full of lots of pictures, full of how to build instructions, parts, recommended parts, and links to those parts. Each one of these has a persistent bit.ly link. So, for example, my performer is always going to be at bit.ly slash KGR, KJ6ER performer. That will always be there. But I do update these files depending on questions I get, typically sometimes once a month. So if you haven't downloaded any of these, by all means, download the most current ones. And they're always free. This is my way of giving back. I do invest a lot of work and energy into these, spent many, many hours designing and testing, but this is the way I give back to the hobby that I love so much. And by the way, one of my antennas, if you haven't heard, ARRL QST antenna design competition winner, the performer. Woohoo! I that was announced, I think, about a week or two ago. I did a nice video interview with KB9 VBR, Michael Martins up there in Wisconsin. That's on YouTube about that. But also, I just heard from the QST magazine today, they're going to post a very detailed write-up on the performer in a coming issue, maybe in the next couple of months. So I'm really excited about that. I was very pleased. And there it is, second place. Yay. In the 80 through 10 meter category, and it looked like I was the only US guy in 80 through 10 meters. First place, boy, that antenna sounds cool. Multi-V rotary broadband antenna. Well, I got to check that one out. But really, really pleased to have entered that contest and won a prize. So I'm really happy about that. All right, so let's talk about these antennas. And I'm going to start off with a little bit of high level stuff, and then we'll get into the specific antennas. But When I got into being a geek and electrical engineer that I am, I do want to understand some of the theory. I'm very pragmatic, though. I'm not too theoretical. I'm not too much in the weeds, but I do want to understand the basic math and physics around the antenna. And when I develop a new antenna, I do take a look at that. Maybe 5% of my development time is trying to make sure I understand that. But then I spend about another good 15% of my time doing the computer modeling. And I discovered this after I retired. 4NEC2 is a program I use. It's got a pretty rough user interface. If you tried to ever to use that program, it's not what I would call user friendly, but boy, does it produce some beautiful charts and graphs, and we'll take a look at those in just a moment. But I spend the bulk of my time here in my backyard, and this is my house here in Silicon Valley. Yes, we live on postage stamps in Silicon Valley. We also get a lot of sun, so we use that to offset the high costs of Pacific Gas and Electric. But here's my antenna proving ground right here in my backyard in Northern California. I spend 80% of my antenna tweaking time there, taking what I learned from the model in the virtual world and applying it to my backyard real world. But most importantly, PODA. That's where I do my real world evaluation. And I've spent many, many times A/B testing antennas with hunters. And I love testing new antenna ideas as well as existing ones with the hunters. And so that's where I spend the bulk of my time testing the antennas in the PODA parks. When I design antennas, I do have three principles. And, I was taught this as an engineer. You always come up with three design principles and make sure they're measurable. First and foremost is performance. And I think that's what makes what I do very unique. And I first of all, I only focus on highly efficient antennas. I do care about radiation efficiency. In fact, it has to be at least 90% efficient or more. So what that means is if you input 100 watts from your transceiver, QRO, you radiate at least 90 watts. If your QRP 10 watts, you want to radiate at least 9 watts. And to be honest, most antennas out there are 30 to 40% efficient. Yes, they're that low, and I'll show you why in a moment. So when you hear a high radiation efficient antenna on the air, it sounds louder because I'm sending out more radiation through the air as opposed to other antennas. So, and they're always resonant. I never use a tuner in any of the antennas. That's another big thing. So performance is number one. Secondarily, I like to use the word elegant because I try to think of the simplest design possible so that it's very effective at what it does, but also it's very fast and simple to deploy, to set up and to take down. I know a lot of guys that spend, 20, 25 minutes setting up their POTA antenna, activate for an hour, then taking another 20 to 25 minutes to take it down. All my setup time is 5 minutes or less. If I can't deploy an antenna in five minutes or less, I don't want to use it. In fact, I typically now, I've been using these antennas for so long, I do it about 3, 4 minutes. You drive, get out to the picnic table, set it up, 5 more minutes later, you're on the air. That's what I love about it. Elegance is what I call that. And third, convenience. Obviously, these are all portable antennas. I got to make sure that they're easy to pack, whether it's my backpack or it's the picnic table, and they got to be relatively light, 5 pounds or less. So that's a big part of a portable antenna. Easy to transport, easy to pack, easy to deploy. 5 pounds or less. And when I first started this, I was designing these antennas for myself for picnic table activations or QRP backpack. But I didn't realize there's such a huge HOA community out there that really wants to set up an antenna like after dinner, work on the air for 2, 3 hours without the neighborhood marshal seeing them and then take it down. I didn't realize that was such a big opportunity, but I would say about a third of my antennas are being used in HOA restricted neighborhoods, as well as emergency communications. A lot of ARES groups have adapted to, for example, the performer antenna. So I'm really pleased to see that. That makes me happy. Okay, I promised a few antenna fundamentals. I'm going to keep it high level. But believe me, these are really important for you to understand because it leads me into why I designed the antennas that I design. All right, so let's take a look at a resonant antenna. You all have your license, so I know you know this equation. Z, impedance, is equal to R, real resistance, plus reactance, X, with a J in front. And what is the J? The square root of -1. It's an imaginary number. Don't worry about it. But reactance is capacitance and inductance, right? In a resonant antenna, for the most part, the capacitance and the inductance offset each other, so it becomes zero. So resonant antenna is just real resistance, R. So when we say a resonant antenna, real resistance, what does your transceiver see when it sees and operates with a resonant antenna? Well, here's your transceiver putting out your 100 watts or 10 watts or G90 20 watts. It sees two resistors in series to ground. That's it. It sees two resistors in series to ground. That's how you model a resonant antenna. And just like many things in life, you have good, you have bad. You have yin, you have yang, right? There's a good resistor and there's a bad resistor. The good resistor, you have less control over it because that's inherent in the antenna you use. That's called radiation resistance. So, for example, a quarter wave antenna, like the Performer or any quarter wave antenna you use, is roughly about 37 ohms, plus or minus. It depends on the configuration, but for the most part, it's 37 ohms. If you have an elevated dipole, horizontal, fed in the middle, it's about twice that, about 70, 72 ohms. So that's the radiation resistance. That's based on the type of antenna you are using. Okay, so given that you don't have a lot of control over that, it is what it is. Then there's a bad resistor. So the good resistor helps you radiate power in all directions. That's productive. But the bad resistor, it's called loss resistance. That includes any kind of losses in your conductors, insulators, loading elements, but most importantly, all that potential radiated energy that's going into the ground. You're heating up the dirt. You don't want to do that. You want to minimize that as much as possible. That's wasted energy. So why are these two things important? Because those things, after a full page of calculations, ends up with a very simple equation for radiation efficiency. It's just the good resistor, that's the radiation resistance. Let's say it's a quarter wave antenna, about 37 ohms, over the sum of those two resistors, the good resistor plus the bad resistor. So when you look at this equation, it becomes really clear if you want to optimize your radiation efficiency, you want to minimize your loss resistance. You want to minimize the bad resistor because the bad resistor, all that energy that could potentially be radiated is being converted to heat. It's wasted. Is that clear? Everyone get that equation? Pretty straightforward. You've probably seen it before, but this is why it's so important because these are the things you care about when you deploy portable because you want to get as much energy out into the ionosphere as possible. All right, here's the slide that always seems to shake some people up in a good way, I think. It's also the type of research I did back in 2020 before I got on POTA and before I started designing antennas for myself, portable antennas. When I first went out in my backyard and said, okay, I got to make sure I have a quarter wave antenna, I did it like everyone else does. I took my feed point, I put it about an inch or two above the ground on a spike or a little mini tripod, and I threw out a bunch of quarter wave or equivalent radials around it, 2, 4, sometimes 8, it depends. When I found out how inefficient that antenna was, I said, oh my gosh, I don't want to use this kind of antenna. There was a brilliant guy called John Oppenheimer, much smarter than me. Back in 2013, he published this and he really, really shook up the community because people didn't realize how much loss resistance there is with radials on the ground. So take, for example, let's take a look at the chart. This column is the number of quarter wave or quarter wave equivalent radials. So when you say there's two, it could be 2 quarter wave radials or it could be 4 eighth wave radials, right? That's what we mean by equivalent. And these are ground radials. They're on the surface, right? Grass, dirt, concrete, whatever it is. Let's just take a look. Let's start at 2 radials on the ground, one pointed north, one pointed south, or east and west. It has a loss resistance, that's the bad resistor, of 85 ohms. So you go, well, 85 ohms, come on, Greg, that's only 85 ohms. That's not very much. Well, plug it in that radiation efficiency equation. Your quarter wave antenna is 37 ohms, right? That's the inherent resistance. That's the radiation resistance. That's in the numerator. You put it over 37 plus 85 ohms, which is 2 radials. What do you get? You get 30%. 30%. You put in 100 watts, you radiate 30. Will you get good SWR? Absolutely. You can get perfect SWR. Will you find a resonance that you want on the band? Absolutely. Will you make contacts? You will make contacts. But can it be better? Absolutely. It can be much, much better. Let's just take a look at what from what I see, most POTA activators use when they use a quarter wave antenna. They typically use 4 radials, quarter wave or equivalent radials on the ground, one at each compass point. That's 63 ohms. Let's go to the next point. That is only 37% efficiency. So you throw out 4 radials, even if you throw out 88 radials, you're less than 50% efficient. You're only radiating 47 watts of your 100 or 4.7 watts of your 10. I mean, you can do so much better. In fact, it takes at least 32 radials, which isn't too portable. Now, maybe for home use, it's okay, but it takes at least 32 radials to get 70% efficiency. In fact, it takes 64 radials to get over 80% efficient. Now, home use, especially if they're buried in the ground, that's a good idea. Portable use, not practical, not pragmatic. Doesn't make sense. And to give you some perspective and why I got so excited about elevating just 2 radials, in all my research and all my computer modeling and field testing, 2 elevated radials at 36 inches above the dirt, above the ground, the grass, the loss resistance is only 4 ohms. Plug that in your equation. 37 over 41 is 90%. So when I got on the band, when I first designed my prototype performer antenna and I got on the band, I kept hearing comments like, "You're the loudest signal on the band. How many watts are you running, dude?" I said, "I'm only running 100 watts, but I'm radiating 90 next to these guys who are probably radiating something like 30 or 37% or 30 to 37 watts. That's why I sound so much louder. And that's why I'm a big believer in elevated radials. And you only need 2 of them. You don't need 64. In fact, if you look at this, 90%, where do you see 90%? It takes about 100 radials on the ground to get you 90% versus just 2 elevated. You tell me which one makes more sense for portable activations. Then there was another brilliant guy, again, much smarter than me. You've probably heard of Rudy Severns. He put out this amazing series of articles in QEF, which I think was a technical form of QST, about 25 or about 15 years ago. He said, all right, I've heard a lot about these elevated radials. I'm going to do my own very sophisticated experiment. And he did an amazing job. And you may have seen these couple charts. He said, all right, let me go on 40 meters because he loved 40 meters. Let me put 4 quarter wave radials on the ground on 40 meters. And let me take a field strength meter and go out about a wavelength. And so you can see this took a lot of work. He threw 4 radials on the ground, took a measurement about a wavelength away, and that was his 0 dB point. So he normalized everything to 4 radials on the ground on 40 meters. So what he did is he went to 4, he went to 8, 16, 32, and then 64 and measured what the radiation strength was relative to 4 radials on the ground. And he found when he got up to 64 radials on the ground, 40 meters, he got about a 6 dB improvement, So that's about an S unit in the near field. That's pretty significant. All right. So he was pretty pleased with that. And that makes sense. The more radials you have on the ground to return that radiated current back to the feed point to be re-radiated, the better. That's what you want. Then he said, okay, let me take those same 4 radials. So here's on this chart, the x-axis is radials and the y-axis is gain improvement over 4 radials on the ground. He then said, let's take those 4 radials and instead of adding more radials, let's elevate them off the ground. So he's taken those 4, and believe me, these are 33-foot radials, and he's got 4 of them. He has to elevate them, so it's not a simple task, but he did it. He did a fantastic job. In fact, he was so amazed by these results, he said he ran it multiple times to verify the results were accurate. just 6 inches off the ground. When he raised it, the 4 radials just 6 inches off the ground, he got a 5 dB improvement in signal strength. 5 dB. Once he got all the way out, this is 1 foot, 2 feet, 3 foot, 4 feet off the ground, those same 4 radials, he had a little bit more, about 6 dB improvement of over 4 radials on the ground. So he was pleasantly shocked. And the bottom line, his conclusion was 4 elevated radials on 40 meters at a height of 4 feet are equivalent to 64 quarter wave radials lying on the ground. This was a huge, huge study. In fact, it was incredibly popular back in the early 2010s. People saw this and they were just amazed at his results. Fantastic. So why is that? Well, think of it this way. Think of the ground and your radial as 2 plates of a capacitor. So let's suppose your radial is 1 plate, the ground is the other plate of your capacitor. For those of you that may or may not remember your physics class in high school, what happens as you move the plates further away from each other? The distance between the plates is inversely proportional to the capacitance. And in this case, capacitance is not your friend, because when your radials capacitively couple to the ground, all that potential radiated energy, that current, is going into the ground instead of out your radiator. So that's why just moving those 4 radials up to 6 inches made a huge difference, because it's inversely proportional, the capacitance is, to the distance between the 2 plates. The other important reason, when you look at a dipole, and here's a chart, you probably saw this on your exam, when you have a resonant dipole at a resonant frequency, it creates a standing wave with current and voltage 90 degrees out of phase. In fact, your current maxima is at the center of your half-wave length antenna, and that's where your voltage is at its minimum. Here's your current in red and your voltage in blue. And at the ends of antenna, you have very low or negligible current and very high voltage. In other words, don't touch the end of your radial, because you'll get a little bite. I had one unintentionally when I was out adjusting my radials, and one of my colleagues queued up the microphone when he shouldn't have done that. So, all right, so your current maximum is in the middle. So let's pretend this is a quarter wave antenna, right? A quarter wave antenna is basically, let's just take the left side of this dipole and put it up at a 90-degree angle. When you have a quarter wave antenna, that is half your dipole standing straight up, but the other half of your antenna is your radial. That's the other half of your antenna. And when that radial is on the ground, especially right in here on the ground, look at all the current that's in that radial. High current. And what radiates electromagnetic waves? Is it voltage or is it current? It's current, not voltage. Current radiates, not voltage. So when you have this radial on the ground with all this current in the radial, especially in the first half of it, this is all this huge energy that you're losing into the ground instead of being radiated out of your antenna. And that's why when you elevate your radials, you're at least 90% efficient, because you have a huge gap between one plate of that capacitor and the ground, versus when they're touching each other, you're losing all that energy into the ground. You're heating up the dirt. You don't want to do that. Now, if you use a half-wave antenna, and I also got into designing half-wave antennas. Off-center fed is in the hundreds of ohms. If you just move it from here, typically in a dipole, I said it's about 72 ohms impedance. When you move it down here to an off-center fed, you're in the hundreds of ohms. So use like a 4-to-1 on-end, for example. Or if you're at the end, in an end-fed half-wave, very popular antenna, it's in the thousands of ohms. So typically 95% radiator, 5% counterpoise. Here it's about roughly 80% radiator, 20% counterpoise. The reason you don't have to elevate your half-wave antennas as far off the ground, especially the counterpoise, is because you have very, very little current in your counterpoise. So your counterpoise and your feed point, I recommend on a half-wave antenna, your feed point should be at least a foot off the ground. I like to use 2 feet. Your counterpoise can droop down and touch the ground because there's very little current. But if you've got a quarter wave antenna, you got to keep your feed point up about 4.5, 5 feet, ideally, and your radials at least up about 2-3 feet off the ground. That's what I recommend on a quarter wave. Does that make sense? Do you understand why it's important to keep your radials elevated on a quarter wave and it's okay to have your counterpoise on a half wave down? It's all about the current, or in this case, the lack thereof. Any questions before I get into the antennas? You guys get that? I love that. Okay, good. Let's talk about the award-winning performer. I like saying that. I just started saying that 2 weeks ago. It's kind of fun. It comes in multiple flavors. The bottom line, the performer is had a cute name. You know, I came up with cute names just because it's fun. Performer is portable, elevated, resonant. Portable, elevated, resonant. It's either deployed on a tripod or it's deployed on a PVC tube with a spike at the bottom. Either way, it's a very effective antenna, heavily computer modeled. In fact, I spent about a month using 4NEC2 computer modeling the performer before I actually took it into my backyard and tried to build it because I checked everything. I checked how high do the radials need to be, how far apart do they need to be, what's their span, what happens when they're opposite each other, what happens when they're 90 degrees apart. I checked different numbers of elevated radials all the way from 1 to about 8. 8 was too many. 1 could be better if it was 2. I checked spans of the radials, whether they're opposite each other, whether they're 90 degrees, whether they're 20, whether they're 120. So there's a lot of things to check, a lot of permutations and combinations to verify. But I ended up with the end result being 2 elevated radials, either 90 degrees apart for some modest gain between the span of the radials and front to back, and also 180 degrees if you want it omnidirectional. The fundamentals of this is just a little simple pictorial of the antenna, but it's pretty straightforward. Your radiator is a 17-foot telescoping whip. I like Chameleon, but I've used MFJ. I used to use Wolf River Coil, but now Chameleon and Alpha Delta and quite a few others have a lot of telescoping whips out there. But if you want to get all the bands, you want 17 feet. It sits on a mirror mount. And again, I tried to make this a simple antenna with simple and relatively inexpensive parts you could buy on Amazon or Harbor Freight, or you may already have in your ham radio stuff box. It sits on a mirror mount. The mirror mount can either be on a tripod or in this case, it's a PVC tube. You see it's up about 52 inches, which is ideal in my mind. It has to have a choke. Never operate any of these antennas, especially the quarter wave, without a choke. If you don't use a choke, I don't care what your SWR is, you just added a third radial, which is on the ground because of the coax shield. Not only do you ruin the efficiency of the antenna, but you mess up the radiation pattern. You'll definitely mess up the resonance. Who knows what it's going to be. And you'll also generate common mode currents, and you could generate RFI back in your shack, or in this case, back at your operating position. So always, always use a good quality RF choke. And I like the coax wrap toroids, which I'll talk about. The radials are just simple, what I call elevated, tuned, linked radials. Elevated, obviously, off the ground from about 52 inches, roughly 36 inches off the ground. They can be downward sloping a little bit. They're tuned to the band. So, for example, if you're on 6 meters, you adjust the whip to resonate on 6 meters, and it uses the first 43 inches, of the 2 elevated radials. I count the Muller clip, which is clipped onto the mirror mount, about 1.5 inches, but it's about 43 inches. And then you adjust your whip, and you're on 6 meters. If you want 10 meters, it's just another 37 inches. So rather than having a second set of radials, I just put an incremental segment on the 6 meter radials, another 37 inches. So now you adjust your whip a little bit longer, and you've got 2 80-inch radials, elevated radials, and so on until you get out to the 20-meter band. Now, there's 2 ways to change bands. There's a hard way and there's an easy way. They both work. Obviously, you want to use the easy way. When I first started, I used the hard way because I didn't know better. But then I thought more about it, and then it hit me one day about 6 months after I built the antenna. Oh, there's a much easier way to change bands. So let's say you're currently on 20 meters, and you want to go to 10 meters because the band looks open. What do? Well, the hard way, you would disconnect this segment, this segment, this segment, and that segment. So you're only down to the 10-meter radials of 80 inches each. You pull these stakes out, you move them back in, you reclip it, and then you're on 10 meters, adjust your whip, and you're ready to go. Will that work? Yeah, it works great. Uh, is it easy? You have to move these stakes in and move them out. I don't like that. And then all of a sudden, one day, 6 months into it, it hit me. I had this epiphany to say, there has to be a better way, and there is. I just created a 4-inch non-conductive segment, and I put little spade connectors on each side. In this case, I'm using paracord. You can use that weed whacker plastic string as long as it's non-conductive. You take these things, and I typically store them here at the end of the 20-meter segment. But let's say you want to go to 10 meters and you already have these 2 stakes out for the 20-meter segments. You leave the stakes where they are. You just unspade connect the little non-resonant segment from here, and you put it between, in this case, the 10 and the 12-meter band. This antenna will see these two 80-inch radials, but then it sees the non-conductive segment and says, oh, I guess that's the end of the radial, so I'm done. It never sees the other radials segments out there. So if you want to build the performer and you want to do it smartly, I recommend you put together some. I use 4 inches. Some guys use 2 or 3 inches. They all work, but I want to be safe, especially running at 100 watts. So I used 4-inch segments, and I put spade connectors, and I just insert them in between the 2 band segments that you want to operate on. Does that make sense? Is that pretty clear? I assume that's the way Sam does it, right, Sam?
Well, yeah, so just to point out, because I was handing out my radials, I got the one, I have the version before you had the Epiphany, so this is the hard way. It still works, but it's not the version that's current that you got here.
Roger,
But Sam's smart. He's learned something tonight.
I have, yeah. This is a better way to do it.
That's what we're here for. We're here to learn. Go ahead, Becca.
I don't know if you can see this, but this is my implementation. I have a Lego piece, got holes in it. It provides stress relief, and when I want to disconnect, it's simply a matter of undoing that alligator clip.
Yeah, very good. Yeah, very good. I love that ham-engineering. It's amazing.
I tried your way first, but the spade connectors hurt my fingers, so I was looking for something to do.
Your delicate little fingers? What do you have, long nails and that sort of thing? Come on, Becca, let's see the nails.
I also have a surplus of Legos in the house.
Yeah, I know. I've got all of our kids left them behind, so I know what you mean. Yeah, no, that's great. In the end, basically every person that's put a performer together kind of gets this basic design. This is a reference design is what we call it, and they make it their own out of the stuff they have and whatever they enjoy doing. So yeah, that works. Good idea. Good job. Any other questions on this before I move? Good. Okay. I mentioned it comes in a couple of flavors, actually 3, but here's the one on a tripod. I use a polar duck tripod. In fact, it was I recommended it so much it got sold out on Amazon, but there's a couple other brands that look just like it, probably all made by the same company, just they put their own label on it. So it's about $50. I really, really like this tripod. If you don't have a good tripod, consider this one. It's extremely lightweight, extremely lightweight. It folds up. In fact, I'm backpacking this up on a hill tomorrow. And what don't you see in the middle? You don't see a span. You don't see a plate that limits the span of the legs. So even when it's extra windy, you can spread these legs out further, and it's fantastic, incredibly stable. All these legs are telescoping. It also now, Sam has that telescoping pole above it. You probably can't see it, but you don't need that aluminum tube there anymore. But the aluminum tube works. That's the way I started when I had the old polar duck. If you look at it, I use the Chameleon 17-foot whip. Here's your classic mirror mount. There's your coupling nut. And notice here's the Muller clip, and I have the 2 elevated radials coming together with one clip, and I just clip it onto one of the screws on the mirror mount. That's all you need to do. And then there's the choke right there. And then at the end, that's where I typically store my, in my case, my paracord insert. I put it at the end. When I want to change bands, I just move it in to whatever band I want to operate on. That's the tripod mount. Here's the PVC mount. This is the way that I like to use it. The reason I like the PVC is because there's no metal around around the performer antenna. Uh, Especially on 6 and 10 meters, some of those shorter radials would interfere a little bit with a tripod. I mean, negligible, not much, but being a geek, I wanted no interference, and so I switched to the non-conductive PVC tube, furniture grade. At one end, I put a 3/8 by 24 bolt, and which then can screw into a chameleon spike or a little mini tripod, in this case, the WRC Megapod. At the top, I have a 3/8 by 24 coupling nut and bolt. And then I made a little jig where I took like a little threaded rod, put it into the coupling nut, put the a mirror mount on top of that. You can see the coupling nut for the whip is right there, and the choke is on it. And this is the way I store it. This is the way I bring it out. It's ready to go. I get in the field, I just spike it in the ground, put in my whip, put in my coax, put up the radials, and I'm done. It's that quick. And I love that. I typically in the PDF I give you all the measurements because these have all been computer modeled and verified in the field. In fact, tweaked in the field over time. They're all labeled. You can see Muller clips at the end of these two radials labeled. I use a Brother label marker. Just you have to label them because you don't want to get them mixed up. If you don't have good spade connectors, strong recommendation for Wi-Fi. I love these things. Not only do they have heat shrink tubing, but they have internal glue, so the fit remains very tight. In fact, the same spade connectors I used back in 2021 are still in the field, still being used. And I've hooked them and unhooked them many, many, many times. So they're wonderful spade connectors. I mentioned the non-conductive segments to insert between the radial lines you want. I roll them all up and put a Velcro little tag around them, or I put them on a kite winder. You get those for like $1 on Amazon. And here is an actual what I take in the field with me. I use these zippered clear plastic bags, which are toiletry bags. And in this bag, I have my radials, my trusty Rig Expert stick. Love that thing. I use my Byberry multi-tool because sometimes you need that in the field. And, you know, I started out using a Sporty 40 for 40 meters, and I upgraded to the Chameleon M coil, and I have a picture comparing the two. They both work effectively, but I love the small size of the Chameleon M coil and the super lightweight. It's a great form factor. I also have a portable version, and I've taken this in my backpack quite a few times when I do QRP. You can see it's a slightly narrower tube, but I cut it in half with a coupler at the bottom. Pressure fit coupler, the same connectors at the top. And I take instead of 4-foot rods, I cut them down to 3-foot so they fit in the backpack easier. Here's my ICOM 705 backpack, which I love to use. Inside, I put the radials, the stick, the M coil. I use Messi and Poloni coax because it's well made, extremely low loss, and I hate to lose any energy in my 50-foot runs or 25-foot QRP runs. So I use Messi and Poloni. Also used a ABR Industries US cable. I've used them before, but these guys, I think they have better connectors. My ABR connectors failed on me a couple times. And this is what I backpack with out in the field running QRP. And here is the Sporty 40 meter coil. Here is the Chameleon M coil. You can see the size difference. That's why I love this so much. It's so well designed. It works incredibly well. And everything fits nicely in my ICOM backpack. All the numbers, these are all computer modeling numbers. They're all in the PDF. The bottom line, average across the 6 bands, 20 through 6 meters. Very high efficiency, over 90%. SWR, very low. I typically in the field get less than 1.10 to 1 on all the bands. It's that good. Excellent reflection coefficient. Anything lower than minus 20 dB is fantastic. When you put the radials 90 degrees apart, you get modest gain, about 4.4 dBi. But you get a front to back, about a about a 3 dB front to back, which means double the power between the span of the radials at 90 degrees versus the back of the antenna. So it's somewhat directional, but you get a front to back, so you can kind of eliminate some of the noise behind you if that's what you want to do. The takeoff angle, or what they call the peak radiation angle, about 24 degrees, perfect for regional communications and a very respectable beam width. You know, the tighter, the smaller the number that is, the more concentrated the signal. So 24-degree takeoff at a 44-degree beam width, pretty darn good. The model generates some beautiful pictures. Of course, great SWR reflection coefficient. This happens to be 15 meters. You can see the radiation pattern when the radials are 90 degrees apart. Here's the side view in blue, and here's the top view in red. But the 4NEC model produces these amazing graphics, and I love these as a geek. The purple and the red are your strongest radiation, and if you look carefully, this little white line and this little white line here are the two elevated radials. And you can see how the red and especially the purple is the strongest between the span of the radials. But most importantly, you look at it here from a side view, you can see here's the purple, here's the red, and here's all that energy going out between the span of the radials at 90 degrees. And it also has this interesting extra energy at higher angle radiation for some very regional coverage as well as some NVIS. That's why this is a popular antenna for emergency communications as well. But most importantly, here's the real world, and this is the first week I took the antenna out to California Park. I took all these pictures and measurements, and I was blown away on every band. I want you to notice two things. One, how low the SWR is, but two, how broad banded it is. In essence, you can get the entire 20-meter band at about 1.3 to 1 and less, the entire 20-meter band. So whether you're up here in sideband or down here in CW or digital, you don't necessarily need to move the whip because, my friends, I want you to look over here to the far right. And if you can see this on the big screen, this is SWR efficiency. When you've got an SWR of 1.50 to 1, you're only reflecting 4% of your power. So in essence, it's 96% efficient, your SWR. Don't use a tuner. I don't recommend anyone using a tuner if you've got an SWR of 1.5 to 1 or less. You don't need one. It just adds a little bit of insertion loss and some other issues potentially. Don't use a tuner. And I guarantee you these antennas are all going to be 1.50 to 1 or better on all of the bands. So no tuner required on 20, 17, 15 meters. Look, the entire 15-meter band is 1.2 to 1 or better. The entire 15-meter band. That's crazy, right? Crazy good. Very flat, of course, on a very narrow 12-meter band. The 10-meter band, this is using the tripod. If you use the PVC, the 1.2 gets to be more like 1.1 or less, but still 1.2 is fantastic. Whether you do sideband here, CW digital, or FM up here, you can just shorten your whip a little bit if you want to do some FM on the calling frequency up here. I've done that, and I've worked across the country on, and even to Japan and Australia on 10-meter FM from California. 10-meter FM. It's pretty amazing. When the band's open, it's pretty amazing. And of course, the very broad 6-meter band, look at that. You get about 2/3 of the band, 1.5 or better. But you can do your SSB calling frequency here or FM there. You just adjust the whip if you want to. That's the real world. And that's what's most important. I always get asked what happens when you change the span of the radials from 90 to 180. 90 degrees apart is the red. 180 degrees apart is the blue. Let's take a look at some of the numbers. At the takeoff angle of 24 degrees, when you're in the 90-degree span, you get, this happens to be on 15 meters. I just picked one in the middle. 0.31 dBi of gain between the span of the two radials. When they're in the 180-degree span, it's an omnidirectional antenna. And if you're in the center of the country like Texas, and you're not trying to go for the East Coast, the West Coast, South America, or Canada, you want omnidirectional coverage, it's minus 0.67 dBi all around, which is pretty typical of a quarter wave antenna. The difference is with elevated radials, you're getting over 90% efficiency. So you're getting just about all of that gain. So you get about 1 more dB of gain between the span of the radials versus omnidirectional. So it's a little bit. That's not bad. Regional coverage Typically, when we say regional coverage, we're talking roughly 400 to about 1,500 mile distance, which is perfect for parks on the air. That's typically between 30 and 60 degrees takeoff angle. Look at the extra energy you get when your radials are 90 degrees apart, the red versus the blue. You get all this extra energy in the regional coverage. And again, that's why this is so popular for parks on the air, because this is working, you know, 1 or 2, 3 states over. A lot of times that's what you want, especially if conditions are wonky like they've been lately. And NVIS is anything from 60 to 90 degrees. 90 degrees is your classic cloud warmer. But 60 degrees is respectable emergency communications, 60 to 70 degrees. Look at all the extra energy you get when the radials are 90 degrees apart. So it's not just getting a little front to back between the span, you're also getting some extra energy in the regional and the NVIDIA coverage as well. Any questions on that? That's the award-winning performer. So we get to the half waves. Let's do it. In fact, today I was out and the band conditions were really, really tough. But I got 90 QSOs on my Challenger off-center fed antenna, and I was very pleased. I was on 15 meters and 20. 10 and 12 weren't open. I always start on 10, work my way down, but they weren't even open at all. 15 was rough, but I did about 30, 40 on 15 and the rest on 20. I avoid 20 if I can because it's so crowded. But on rough band days like today, I had to go to 20 so I can get more QSOs. But let's take a look at my off-center or my half-wave antennas. Now remember this chart. This is the only geeky thing I'll show up front. This is the same chart I showed you before. Here's the number of quarter wave radials, the ground loss. Here's the quarter wave efficiency. Same chart. I just added 2 more columns. I added what I call an off-center fed efficiency and a end-fed half-wave efficiency. And if your radiation resistance of a quarter wave is about 37, on your half wave, off-center fed is in the hundreds, as I mentioned earlier, end fed is in the thousands. The only reason I'm showing you this is just for a mathematical exercise. Remember when I showed you that equation, I said it's your radiation resistance over the sum of your radiation resistance plus your loss resistance. And I said you want to minimize your loss resistance as much as possible. The other option you have is to increase your radiation resistance with a half-wave antenna. Now, let's just pretend this is not the case, but let's just pretend you have one radial on the ground, which a lot of people have done. I've seen a lot of those deployments. I think Chameleon has a couple of antennas where they just have one radial on the ground. The ground loss is 104 ohms, 104. So on a quarter wave antenna, that's 26% efficient. You're radiating 26 watts out of 100. Okay, pretty bad. Let's just pretend it's not, but let's just pretend your counterpoise, your single wire counterpoise on a half wave is also 104 ohms. By just increasing the radiation resistance to a half wave in the hundreds or thousands of ohms, your radiation, even with that same lossy single radial on the ground, you go all the way up to 96%. But here's the reality. Remember I said earlier on that with a half wave counterpoise, you have very, very little current in that counterpoise, so you can have it on the ground because you're not going to have any loss resistance or very low loss resistance. As a matter of fact, in all my testing and modeling, a single counterpoise wire on a half-wave antenna, one of my half-wave antennas, is 12 to 25 ohms. And if you plug those in, you're going to get over 90% efficiency. And we'll take a look at those now. Okay? So let's take a look at the Challenger and Dominator. These are 2 versions of a half-wave antenna. One is off-center fed using a 4-to-1. One is end-fed using a 49-to-1 or preferably a 56-to-1. I'll show you that in a moment. These are here in my backyard on the polar duck tripod. Look how compact they are. This is the way I take them to the field. What I do is I already mount the mirror mount and the unun to the tripod ahead of time. And you can see the choke is sitting there as well. And there's the radials all, or the counterpoise all wound up. And there's the Chameleon 25-foot whip. Very compact, very small. It takes me less time to set up one of these antennas than the Performer because you don't have to elevate 2 radials. Again, I computer model them extensively and very lightweight and fast to deploy. Let's take a look at a pictorial of the off-center fed using a standard, very common 4-to-1 from LDG. LDG makes a pretty good, I would say it's pretty good. It's not great, but it's pretty good 4-to-1 Anand, reasonably efficient. It's the same setup. In this case, now you're using a 25-foot whip. You can use a 17-foot whip. You just can't get the upper bands like 20 and 17, but you can still use the 17-foot whip. Again, to the mirror mount. In this case, it's attached to the upper portion of the tripod. I've got a little pigtail. I use a, you can see here like a little ring connector with a bolt to the base of the to the mirror mount. A pigtail about anywhere 6 to 12 inches. I think I spec 12 inches to the positive side of the Anand. And I take another 6-inch pigtail on the ground side of the Anand. From which, once I get into the field, I just attach the counterpoise segment that I want to, the band I want to operate on, and it's ready to go. And just like in the quarter wave, you got to have an RF choke. You have to use an RF choke. You don't want the counter, or in this case, the coax shield to be a second counterpoise wire. Not only will it mess up the SWR and resonance, it will not give you that great low angle of radiation and propagation pattern that you get with a really well-made half-wave antenna. The half-wave, which I call the Dominator, the Challengers, the off-center fed, the Dominators, the end-fed half-wave, uses a 49-to-1, well-made by 10 Tennis. Get these on eBay. And instead of, so everything's the same except it uses a 49-to-1, and it's the same kind of little pigtail segment off the ground, and you still got to use a choke. This will get you 20 meters to 6 meters, the off-center fed, because it's an off-center fed. The radiator is not as long as the end fed. The end fed will get you 17 meters because you're limited by your 25-foot whip. And a 49-to-1 or 56-to-1 will never get you 6 meters. That's just the way it is. A 4-to-1 will. So you can go 20 to 6 here. You go 17 to 10 with this one. The PDF gives you all the segments, and it's just like a radial. These are all linked counterpoise segments, one for each band. And yes, you can use the Lego, or you can use the paracord segment in your counterpoise line. So your antenna only sees up to the paracord insert and doesn't see the rest of it. So it still works. And also for the Dominator end-fed half-wave, it's the same thing. Counterpoise links are all in the PDF. But you can see here, here's the mirror mount. There's the, in this case, I'm using a 12-inch pigtail for the positive side of the Anand. Here you'll see the 6-inch pigtail for the counterpoise, all mounted, ready to go. So all I have to do is attach the whip, attach the coax, and attach the counterpoise segment I want. And here it is with the 49-to-1. Now, this is where I get geeky, but you know, this is really important stuff. And I bought quite a few 4-to-1 Anands, different brands, and quite a few 49-to-1s and 56-to-1s. And what you're only seeing are the best of the best. That's what it takes. It takes a lot of trial and error to figure out which one works the best. But LDG, this is relatively inexpensive. And I figured, you know, if you want an entry-level off-center fed half-wave Challenger antenna, you get the LDG. It's $30. Insertion loss, and I measured all these on my own Nano VNA back-to-back, so multiple times. I know they're fairly accurate. The Anand is about 92.4% efficient, so you're not really sacrificing a lot to match that 200 ohm impedance at the input. It's rated at 200 watts and bandwidth 1.8 to 30 megahertz. Spec. It does work on 6 meters. Not great, but it works on 6 meters. When it's open, it's not a big deal. I love this. One of my favorite ham radio companies is Palomar. They're based in San Diego, probably near that barbecue joint that one of you guys mentioned. It's only $30. It's got very low insertion loss, 97.3% efficient, rated at 1500 watts. Strong recommendations for the Palomar JC1 1500. It'll probably cost you a little bit or almost that much just to build your own, but they do a phenomenal job using an FT 240-31 toroid. That means it's 2.4 inches from here to here. That's what the 240 means. But if you want to be a geek and be like me and squeeze as much radiation out of that antenna as possible, I strongly recommend for the Challenger Plus, I call it, because it gives you extra radiation efficiency. Palomar makes this what they call a bullet 4-to-1 unknown, and I'll show you the inside in just a moment. Very good insertion loss, 94.6% efficient. Spec'd up through the 6-meter band, does a fantastic job. They also have an upgraded choke. The Palomar MC1 550, $70, extremely low insertion loss. But look at the difference in noise reduction. This is a minus 42 dB rejection versus minus 32. They're both really good, but this really gives you a lot of alleviation of common mode currents and RFI on your coax. So if you look at these combinations, there's really three that you can pull out of this. You get a $60 combination, what I call my entry-level Challenger, the LDG and the Palomar. You get the high-end version, the Challenger Plus, using the $70 Palomar 4-to-1 and the $70 Palomar choke. Or what I know a lot of folks do is they take the better Unknown, the Palomar Unknown, and they match it with this one. So you have $60, you have $100, or you have $140. Your choice. Or you use whatever you have on hand. But these are the ones that I've spec'd and measured. Now the same thing with the Dominator, the NFET Halfwave. I checked out a lot of 49-to-1s. One of my favorites you can buy on eBay from a guy who hand makes these in Tennessee, 10 Tennis. He does a very good job for $45. He ships it to you right away. Lots of great support. But I want you to notice something, and this is true in just about every 49-to-1 NFET half-wave antenna out there. Look at the efficiency on a 49-to-1 transformer, or unknown, same thing. It's only 80%. It's only 80%. So yes, if you use this particular transformer on my Dominator antenna, it doesn't meet my 90% minimum, but it's still, for a 49-to-1, 80% is pretty darn good. So I spec'd it, and I spec'd it with the same Palomar $30 choke, but you can do better. And so I created a Dominator Plus, and in addition to Palomar engineers, my other favorite ham radio companies from My Antennas, they make this amazing 56-to-1 transformer, only 0.4 dB insertion loss for an efficiency of 91.2%. Believe me, that's a big difference, 80 to 91.2. Yes, it costs more. It's roughly double. But if you're really serious about a low-angle global domination antenna for DX, this is the way to go. In fact, this is what I use at home on my sloper in my backyard. I use a My Antennas 56-to-1. Love this thing. Rated at 250 watts. Match it up with a Palomar. So again, you've got three options. You've got this for $75. You've got this for about $120. And this for about $160, depending on what you want. So in both cases, I have the normal version and the plus version. And the plus version just means more radiation efficiency. But let's open them up because we're geeks, right? Here is the LDG 4-to-1 using the 140 by 43. That's 101.4 inches from here to here. It's a 43 mix is what you want for high frequency bands. The inside diameter is about a little less than an inch, about 0.9 inches, and it's only about a half an inch thick. So it's your standard toroid for a like a 4-to-1. It's not bad. It works fine. But the Palomar takes it way, way beyond. They use a dual port bead, and this bead is 1 1/8 inches high and 1 1/8 inches wide. And they drill two holes in here, and they wrap the wire inside those two holes. So it becomes much more efficient and much more broadbanded, much more broadbanded. Here is their high-end choke, and you can see the differences. They use the same very large bead, and they wrap their wire around it about 13 times to choke off any common mode currents or RFI on your line. Let's open up the 49-to-1 10 tennis. Again, he hand makes these. He does a great job. He's got great spacing between the turns. He's got a high-quality capacitor. In this case, it uses a 240 by 43. That means 2.4 inches from here to here, 43 mix. It's got a 1.4 inch inside diameter, and it's, again, about like this one, about a half inch thick. But here's the pièce de résistance. This is the 56-to-1. It uses a 140/43 toroid, so it's 1.4 inches from here to here, but look at the difference. The inside diameter is 0.6 inches versus 0.3 inches, and it's 1 inch thick, 1 inch thick versus a half inch. In fact, I know guys that take 3 of these, they put them on top of each other to kind of increase the efficiency, and that will work. But you could do that, or you can just buy one of these. It's a very thick 1.4 inch outside diameter toroid. It's equivalent to, on their website, they say equivalent to 3 of these. And I went through the toroidal volume equations, and they're exactly right. So it's a really well-made, very efficient 56-to-1 unknown or transformer. Strongly recommend it. The Challenger Plus, using the higher end Palomar, same counterpoise because it's still a 4-to-1, but because now you're a 56-to-1 on the Dominator Plus, you're further out on the end-fed half-wave because it's a 56-to-1 higher impedance, so you have more radiator, shorter counterpoise. But in any case, this is showing both of them mounted side by side on a tripod in my backyard antenna proving ground. I actually use these to test, and I took this to a park one day with 2 lengths of 50 feet coax and an AB switch, and had fun bouncing between the antennas with hunters and seeing which one sounded better. This one, the Dominator, has a lower angle of radiation, so it got me much more DX than the off-center fed. I also have portable versions, and this is one of the ones I'm taking out tomorrow. I'm going to hike up a mountain, if you will, here in Silicon Valley, about 1,200 feet. Not like Colorado, but about 1,200 feet. I'm going to put this in my backpack, and you can see I have the ununs and the choke all mounted on a short but wide piece of PVC tube. Remember, you don't have to be that high off the ground feet point wise on your half wave, at least a foot. These put them about 2 feet off the ground. And I spike them in the ground just like this, or if I don't have ground to stick the spike in, you can just put it on your Wolf River Coil Megapod or any small tripod like I've done here. And it packs up beautifully in my backpack. And that's what I'm taking up the hill or the mountain tomorrow on QRP. So we'll see what I can do with these lousy band conditions. All the numbers are in the PDF. But bottom line, this is the Challenger, the off-center fed. Structural efficiency, 94.3%, depending on which unknown you use. The LDG, 92%. My favorite, the Palomar, 94.6%. Very, very efficient. Very low SWR average. Great reflection coefficient. The peak radiation gain goes up to minus 0.27 omnidirectional versus minus 0.67 omnidirectional on the Performer. So you get a little bit more omnidirectional gain. The Performer was 21 degrees, 24 degrees takeoff angle. The Challenger is 21, so it's 3 degrees lower. So you get further out, a little bit more DX potential. And the beam width comes down all the way to 32%, so much more concentrated, much more potential energy going out on all sides of the antenna. The Dominator, that's the end-fed half wave. Again, very efficient, but depending on whether you use the 49-to-1 or the 56-to-1, it varies from 80% up to 91.2%. I use this one. I love it. Super SWR across all the bands, strong reflection coefficient. The peak radiation gain now goes positive. So the Performer minus 0.67, the Challenger off-center fed is minus 0.27. This is plus 0.67 dBi, omnidirectional, all directions, at an even lower angle of radiation, takeoff angle, 18 degrees, and an even more concentrated beam width, 28 degrees. The Challenger looks like this, what you'd expect in an omnidirectional antenna, but look at the center now. Keep your eye on this. This is the off-center fed Challenger, omnidirectional. It looks like a quarter wave antenna for the most part, but watch when I switch it to the end-fed half wave and notice what happens to these upper loads. They flatten out. And when they flatten out, you get less energy above, and you get even lower angle of radiation on the end-fed half-wave vertical. So that's why I really love the Dominator when the DX conditions are working well. In the field, incredibly low SWR, but most importantly, look how broad banded. This is the Challenger. This is the one I'm taking up on the hill tomorrow. Look at the 20-meter band, 1.1 across the entire band. You don't have to adjust the whip. CW digital sideband, extremely flat. 17 meters, 15 meters. The entire 15-meter band is 1.1 or better SWR. That's incredible. I mean, that's amazing to me. Very flat on 12 meters. even 10-meter band, whether it's CW, digital, sideband, or even FM up here, you don't have to adjust the whip because you've got great SWR, very broad banded. And of course, the entire 6-meter band is, let's see, 1.2 to 1.3 there. Again, you don't need a tuner. You can do FM, you can do sideband. It's incredibly broad banded. The Dominator, same thing. Remember, you don't get 20 meters because it's end-fed half-wave. I don't have enough radiator in the 25-foot whip. Some guys have used a 32-foot radiator from Alpha antennas. That works, but you got to guy it because that's a long radiator. But if you use a 25-foot whip, you get 17, very flat, 15, 12 meters, and of course 10 meters, extremely flat. And of course, if you just use the 17-meter or the 17-foot whip, you can still use the Dominator just on 10 and 12 meters bands. So great DX potential when those bands are open. Let me just summarize then, comparing the three. The Performer is your quarter wave, Challenger off-center fed, half-wave, Dominator, end-fed half-wave. The Performer is the one that gets you 40 meters. The other two don't. The Challenger off-center fed gets you 20. The Dominator doesn't. Here are the omnidirectional gains. Like I mentioned earlier, the Performer minus 0.67 dBi, off-center fed half-wave minus 0.27 dBi. Makes sense. You got more metal in the air. It's a half-wave antenna. And of course, the Dominator end-fed half-wave plus 6.7 dBi. Takeoff angle, the lower, the better for DX. 24 degrees on the Performer, 21 minus 3 more, 18 on the Dominator. I call the Performer my regional continental antenna. That's why it's so popular for POTA. The Challenger is continental global, and of course, the Dominator with that low angle of radiation definitely is a global antenna when the band conditions allow it. Just a visual. Here's the Performer showing the takeoff angle and the beam width. Here's the Challenger, lower, a little bit more gain at the takeoff angle, tighter beam width, and of course, the Dominator, another 3 degrees lower, very good gain, plus 0.67, even tighter beam width. So it makes a big difference on how you use the antennas and what your objectives are. They're all good. They're just like my kids. They all have different strengths. Use them at different times. I love them all, right? Just like our kids. Overlay the three antenna radiation patterns on top of each other. Zoom in. You can see, of course, at 18 degrees, the Dominator wins with a 0.68 dBi versus Challenger and Performer. But I want you to notice what happens right around, what is that, 30 degrees. 30 degrees off the horizon, the Performer's in green, Challenger in red, and of course the Dominator's in blue. The Performer begins to have a little bit more gain around 30 degrees. That's the regional coverage I talked about. But let's put the Performer in its 90-degree radiate. And this is why this antenna just rocks for POTA. Let's zoom in on the Performer with the two radials 90 degrees apart. The Performer's in green, the Challenger's in red, the Dominator's in blue. Look what happens right around 15 degrees over the horizon. The Performer beats the Challenger, and right around, they beats the Challenger at 15 degrees, and right around, what is that, 24, 25 degrees, it beats the Dominator. That's because look at all this extra. Remember, I talked about this earlier, this extra regional energy it puts out between 30 and 60 degrees on the Performer. So again, it depends on what you're trying to do. Do you want DX or do you want good standard regional continental coverage? Then you go with the Performer. So to summarize, all have 90% efficiency, performance. They all deploy in less than 5 minutes, elegant, and they're easy to pack and transport, convenient. They meet all three criteria. Performer gets you 40 meters. It's your best antenna for regional coverage, 30 to 60 degrees, versus the Dominator. Very low angle of radiation, but it's your best antenna for 5 to 20 degree global coverage. And the Challenger is kind of in between. It takes the best of both worlds. It's my highest efficiency antenna, 94%. That's why I'm taking it up the mountain tomorrow, because the band conditions on QRP, I need all the help I can get. It's really the best antenna for balanced coverage. Any questions on that?
Yes. Actually, I've got a bunch. This has been an excellent, very informative. My first question, why do you need that counterpoise on those half-wave antennas?
Always, always, always use a counterpoise on a half-wave antenna.
Right.
Because now you may have heard of some end-fed half-wave antennas, oh, I don't need a counterpoise, it works just fine. Well, they're using a counterpoise somewhere. Most likely they're not using a choke on the antenna, and they're using the coax shield as a counterpoise. You've got to have a counterpoise. The physics, you need some way for the radiated current to get pulled back to the feed point and re-radiated on all kinds of antennas. And if it's even on an end-fed half wave, the old rule used to be you need about a 5% wavelength counterpoise on a half wave antenna in general for the lowest band coverage. That works. Or you can do what I did, and I do one band at a 10 and one band at a time antennas. And so I have linked counterpoise segments for each of the bands, but always have to have a counterpoise. And if you're not using a counterpoise, you're probably using your coax, which I don't recommend because that gives you very unpredictable radiation and resonance. And every time you move your coax, your SWR is going to change.
But that doesn't really answer the why, but I accept your answer and I appreciate it.
Yeah, the why.
That performer work, and it's impressive. So.
The performer? You're talking about the performer?
Yeah, well, that's the only one of your antennas that we've seen work. Yeah.
Oh, okay. Yeah.
We've tried these others, and so we trust you know what you're talking about because we've seen the thing work.
Well, if we had got into the why, part of it, the physics behind the why, a good chunk of it, the bulk of the why, is probably over my head, but would bore the heck out of you guys because it would take probably a good 30 minutes to go through it. I looked at some of the physics myself. It was 2 pages of integral calculus, and I didn't want to mess with that.
And you hadn't used it in 40 years, so you forgot that.
Yeah, but I have experimented with all different kinds of counterpoises on the half-wave antennas, and they performed much, much better. I did whisper tests, RBN tests. I did Hunter real-world evaluations with all different kinds of counterpoises. They always radiated better and more efficiently with a counterpoise. That in this case, I tune, if you will, to the band of operation. So you still need a wire outside the radiator to kind of, if you will, absorb some of the potential radiation that would not have been absorbed and redirected back to the feed point so it gets re-radiated. So you still need something out there. And if you're not using a wire, you're probably using your coax, which I don't recommend because it won't work that well. That's not good.
And so when you say that on an end-fed halfway, because we built some that were to be portables, this is one of our projects.
Yep.
It's just a piece of wire. We're just tossing a rock up over a tree and dragging the thing up into the tree and then feeding it one end. You're saying that we need to have a counterpoise on that as well.
What I'm saying is, if you want it to perform optimally, add a counterpoise. And in fact, a counterpoise, the old rule, as I mentioned, if you're operating on 20 meters, they say just put like a 5% wavelength on the counterpoise. So that'd be roughly a meter. And you'll get better efficiency. You probably get better SWR and a sharper resonance. So I recommend it.
So you're saying 3 feet of counterpoise would be enough in a lot of cases.
Well, think of it this way. So at home, I have an end-fed half-wave sloper, 40-meter sloper. And what they say, the old rule of thumb, and these super duper experts say 5% of the longest wavelength of operation. So on 40 meters, what's 5% of 40 meters? 5 times 40, about 2 meters. So I have roughly about, it's about 7 feet counterpoise on my end-fed half-wave sloper because it gets 40 meters. It gets all the bands, 40, 20, 15, 10, doesn't get 6. Then I use a tuner on 17 and 12, and it works great. And I have, it's choked, so I don't have the coax as part of the antenna, and I have a 7-foot counterpoise dangling down off the antenna. And I played with different lengths, roughly 7, 8 feet seemed to work best for me.
Okay, I'm going to experiment with that some.
Experiment.
You pretty definitive about what the radiation resistance is based on essentially the feed point. How do you know that? Are you able to measure it?
See, I mean, if you want to be really geeky about it, which I love to be, I want radiation efficiency. So I want to do everything I possibly can to optimize that. And I also really like a
How do
very
you know that the radiation resistance on a center-fed dipole is about 73 ohms? How do you know that?
well, smarter guys than me have measured that. And it's
So,
an
so
all,
you basically looked this up.
oh yeah. Oh,
So
I
there's
had to
a
look at it.
table somewhere. Because
Yeah,
I was thinking it would be 78 degrees, the impedance on the center-fed dipole at the peak point, unless you trip them at about 120-degree angle, then it comes to about 50.
yeah, I mean, it depends exactly where you feed it, and it depends on a lot of other things like ground conditions and near field surroundings. All of those things affect impedance. But in general, theoretically, a center fed dipole is roughly around 72 ohms. And off center fed is in the hundreds, end fed is in the thousands, as you know. So it
Oh,
depends on where you feed it and also your near field surroundings and ground conditions.
all right. Are you able to tell that from Fornec 2 or from EasyNet that it's going to give you a radiation resistance figure?
Absolutely. Yes, yes. And that's
Okay.
how it calculates the efficiency. So my 4NEC2 calculated the radiation resistance, and it also helped me on different ground conditions. Theoretically, in the virtual world, it gave me different loss resistances of those ground conditions. So that's again the virtual world. In the real world, it's going to be something a little bit different because also near field surroundings and other things come into play. But yeah, those are roughly the numbers. And I started in the computer model, and that's what really helped me along. But I also, skimmed over the ARRL antenna books. You'll see, in fact, one of those charts came from the antenna book, the antenna theory book.
I don't remember seeing anything giving me radiation resistance like that. It's always just up and, it was magic. So
It's in there. Yeah,
all
well,
right,
here's the thing. Here's the thing that really amazed me, and there's probably a reason for it. I'm surprised that most antenna manufacturers don't even talk about radiation efficiency of their antennas. I really am. To me,
I'm
that
not
is
surprised at all because the radiation efficiency is so bad. And that's the reason. You
I was
want to
just
get
going to say
right
it's a marketing decision, right? It's not very good.
Yeah.
But I mean, people make contacts and they get good SWR, so I mean they're happy.
All right, so my last question, and I'll shut up for a few minutes.
Don't worry about it.
We've had an awful lot of people move out here from California, and all those guys they have to live in an HOA. And as you noticed, a lot of people want it, and that's been a real key issue for us here. And we're in the fourth largest metropolitan area in North America. So you can imagine that there's a boatload of electrical noise.
Oh gosh, yeah.
And your antennas are all vertical.
Yeah.
So how are you? I saw that you mentioned something about reducing noise. How are you dealing with the vertically polarized noise?
That is a tough one. It's only getting worse. In Silicon Valley, for example, on my sloper here at the home QTH, 20 meters has got 20 and 40 have the most noise for me. The upper bands don't as much. But on my sloper, my 20-meter band can be anywhere from best case S2 noise up to S8 noise. It's from the solar panels, LED lights, everything going on in the neighborhood. That's why I primarily focus on portable antennas in parks because you don't have to deal with that as much. So there's a whole bunch of other. In fact, I never really got into it myself, but I know a lot of guys that spend a lot of time trying to reduce the noise on their antennas. They use all sorts of chokes and beads and everything else to do whatever they can. But you're right, most of it's vertically polarized, so you're limited to what you can do. I know some guys that have used that second noise antenna and they put it 90 degrees out of phase. I believe that's what it is. And so it offsets the noise. You've heard about that. You've got your primary antenna, then you have your noise antenna, and they sell those gadgets where you can shift one antenna outside the other. So you're basically putting the noise against itself. And so it nulls it out theoretically. I've played with those at home. To be honest, the best trick that I've ever used at home is I just use my RF gain, the ICOM 7300. is such a great receiver. I know the Yamaha also has great receivers. I just turned down the RF gain, so the noise level is S1, S2 at the worst. That's not the solution, but boy, it really helps the signal to noise. That's the best trick I've used at home is my RF gain. I turn it down.
Yeah, I found it works a lot better than the digital noise reduction. It's the best tool on there. I'm going to shut. This has been great. Thank you so much for everything.
Oh, no, my pleasure. I love these kind of questions. I wish I had all the answers, but I will say this, that those noise antennas, they look and sound great on YouTube, but I don't think they work that well. I just turned my RF gain down. That seems to work the best. But fortunately, portable antennas out in the field, the parks, I put on preamp 1 and 2. I still don't see the noise. So that's why I love portable antennas out in the park. But I do understand the challenges in an HOA. I have the same challenge here in Silicon Valley. We have so much QRM from everything, the neighborhood, the companies. It's a mess, but we do the best we can. Okay, so I'll finish up. Again, being a geek, I got to tell you one more story about my Dominator antenna. You all know what a parasitic director is?
Yeah.
So I'll tell you about it. So I decided, okay, I want to do something a little bit extra. So I took my Dominator antenna, and you'll see that here in this picture. This is the Dominator. This is the end-fed half-wave vertical using a 25-foot chameleon whip. And in this particular case, before I found my antennas, I used the 49-to-1 from 10 Tennis. But a parasitic director, okay, in a beam antenna, a 2-element beam is typically a director in front of the radiator. And depending on which band you're on, it's a certain distance apart, and it's also about 6% shorter. You can also have a reflector behind it, but I only put a director on this one because, one, a director gives you a little bit more gain than just a reflector, and also the space in between the director and the radiator is a little bit less. So it was more practical to be a home antenna, a field portable antenna. So what I decided to do is take my Dominator, and here, if you can see this on your screen, this is just my regular Dominator end-fed half-wave antenna. Then I designed this PVC structure, and I put another coupling nut at the end of it, and I put a parasitic director, in this case, a second 25-foot whip that's 6% shorter than the radiator. All right, so what do you have to do? A parasitic director, all that really means is there's no coax attached to it. It's just a piece of metal hanging in the air, if you will, next to the radiator. And I wanted a vertical 2-element beam. So I created this PVC structure, and the PDF shows you on how to build one. And it goes 17 to 10 meters. So it's a 4-band 2-element beam, vertical beam. And for each band, you adjust the director or the radiator here, because that has the coax and the unit on it. And then you just adjust the parasitic director about 6% shorter. But you also have to change the spacing for each of the bands, right? Because 10 meters, it's a certain length, 17 meters, it's much longer. So I created what I called a trombone, a PVC tube inside of another PVC tube, and I marked the inside tube. And you probably can't see it on your big screen there in the room, but there's a little black mark here, and that's how I know the distance between the radiator and the director for 10 meters. 12 meters, I pull it out a little bit further, and there's another mark here, 15 and 17 meters. So this becomes a 4-band, 2-element vertical beam using 2 telescoping whips, one being a parasitic director. And here you can see it in the field. This design, I played with a lot of different, this is the simplest design, and this is the trombone inside, which can adjust the distance of this. And also, there's like a little, you probably can't see it here, but there's like a little loop at the end of this. So you can manually rotate this 2-element beam around in any direction. And I got to tell you a story. Well, first let me show you what it looks like, and then I'll tell you the story. Fold it up. It's really, really simple. It's just the Dominator with a second whip. It all fits inside this little 36-inch photography bag. I designed the PVC structure that supports the parasitic director. It's all glued. Here's the trombone, if you will, but it's all glued except in two places. So you can take it apart and lay it flat in your garage or in your car. It sets up extremely quickly. I don't know if you can see it, but I have like a little loop at the end of this, which rests on top of the Dominator mirror mount, and that allows you to pick it up and rotate it north, south, east, west, whatever you want. I bring my great circle map to the park so I can point it if I want to get some DX. You're not going to believe the model. When I modeled this, I was blown away, and this is what got me excited, and I'll give you the story. This is the parasitic director here, again, about 6% shorter. Look at all this massive gain you get between the radiator and the second element, the director. And again, the purple and the red are the strongest areas of radiation. As a matter of fact, this is showing the Dominator 2-element beam in blue and the Dominator in red. You can see all the incremental gain. For example, on 10 meters, you get 4 dBi gain, forward gain, just using a second parasitic director with a Dominator. So it goes from plus 0.67 dBi to plus 4, basically, dBi with a second element. And the story I was going to tell you, one of the first times I deployed this out of the park in California, I looked on the spotting page and I saw this park in Germany, and I thought, well, let's just kind of figure out, see if I can even hit this guy or hear this guy. So I manually rotated my 2-element beam over the North Pole to get to Germany from California. I'll be darned, he gave me a 5.7. We worked a park to park, California to Germany. He gave me a 5.7. I had him 5.3, 5.4, but he gave me a 5.7 in Germany over the pole. Now, conditions were good, but this 2-element Dominator beam, vertical beam, helped me get there over the pole. I was just amazed. Just like the Dominator, it's extremely flat, 17, 15, 12, and 10. It shouldn't be much different than the Dominator. So on this chart, I just added one more column. You can see the Dominator here and the Dominator beam here. The biggest difference is the gain, plus 0.67 to, on average, across those 4 bands, but plus 3.6 dBi. The 18-degree takeoff angle, which is great for DX, goes down 2 degrees lower because of the 2-element parasitic director on front to 16 degrees. The beam width goes from 28 degrees, which is really tight, even tighter, 24 degrees. That's why this antenna works so well as a pure DX antenna. Believe me, potentially we're coming down the top of the cycle. If the band gets open on 10, 12, 15 meters, this is the antenna you want to use for some amazing DX. And I'll never forget that park to park with Germany. That just blew me away. So that's it. Again, all of the PDFs are always in the cloud. They're always free. These links don't change. By all means, if you haven't passed them out, Dave, pass them out, or maybe you have, great, then you have access to all of them. But they're always going to be free because this is my way of giving back. And as I do all these presentations and I hear questions, it makes me realize that maybe I should keep adding more information in the PDF. So that's why I always improve them. Even every month or two, I'm always updating them to make them as best as possible. And if you use them and if you really are happy with the antennas, you're always welcome to donate. It's always optional, but I'm always happy to accept, because I spent a lot of money on a lot of junk trying to test them and see how well they worked with the antennas. So here, let me stop sharing so I can see you guys again. There we go. So there you go. KJ6ER antennas.
Thanks, Mihran. Hey,
Any more questions?
Slides?
Questions, comments?
Can you send this?
Yeah, can you send me the slides so I can post them on our groups so everyone can get the links and everything like that?
So the slides that you just saw are a subset of my KJ6ER antennas primer, which goes into a lot more detail. So if you go to that antennas primer link and download it, these slides are a subset of that. If I went through that whole primer, we'd be here for 4 hours. But basically what I did is, as I was learning about antennas 3-4 years ago. I kept collecting all this content and I kept building up the primer primarily for myself initially until I realized this was of great interest to a lot of other hams. So I created the primer and I put it out there along with my antenna PDFs.
Thank you very much.
Questions?
Any other questions? Any other comments?
This is Sam in and just one thing option that I did for my park activations. I've been in a couple of parks where we had some pretty high winds and the tripod would get blown over. One thing that I did to help deal with that is I changed the base of it. So I basically took a piece of Schedule 80 1 1/4 inch and a piece of 3/4 inch Schedule 40, put the mirror mount on the Schedule 40, and then used some paracord and some stakes, and basically it created kind of a guide, like a guide mast that was super stable in the wind. So that was something one option that I did that I found to be pretty effective if you're in a point in
that will work. That will work. I've got a simpler option for you. On the polar duck tripod, you know that little hook on the bottom?
Right.
Yeah, there's like on the polar duck, you have the tripod legs here, then you have the center telescoping pole in the middle. Well, at the bottom of that pole, there's like a little hook. What I did is I took a bungee cord and I took a little lawn stake, one of those little upside down U's, and I put the U stake into the ground and I hooked the bungee cord from that hook at the bottom of the pole to that lawn stake. And what it does is it's actually holding the tripod tight to the ground. So I've had it in 20, 25 mile an hour gusts. That thing didn't even move. The only thing that bent over was this 25-foot telescoping whip. I mean, it was almost 45 degrees, but the tripod was completely stable. One, because I had the legs at the center position, but because I had the single bungee cord from the center hook down to the ground, and from a physics standpoint, that holds it right at its center of gravity. And so it's very stable. You may want to check that out.
That's
It'll save you from putting 3 guy wires around it.
So I'll ask this to Sam first and you as well, Greg. So how great this antenna is. How much does it cost you to build it?
Well, the most expensive part is the whip from Chameleon. This was $70, but probably the rest of it is, I don't know, maybe $30 more, something like that.
$100 for it.
Yeah, probably. Well, in my case, because at the time I wanted to do 30 because I used CW. I did the full vertical coil so I could trap it for 30, and yeah, so that would be extra.
Yeah, no, so it totally depends on your version of the antenna. Everyone likes to tweak it, kind of like what Becca did with her Legos and such. I mean, it can be a lot more expensive, or it can be relatively cheap. It depends on what you have on hand and how you want to build it. But I think that's a good estimate. The whip is the most expensive part, obviously. If you want to buy a new tripod, that's another $50. But the mirror mount and that's all. The rest of it is you probably have already on hand. Even a choke, you probably already have. By the way, if you don't use a coax wrap toroid and you want to use beads, at least use 5 beads. 5 beads in a row. 5 to 7 is optimal. Anything less than 5, I wouldn't do. Any other questions? I know it's, what is it, 6:30 here, so it's 8:30 out there. Any other questions? Any other comments?
That was a great ride. I enjoyed it.
Good. Well, thank you so much. Really do appreciate the invitation. I appreciate the time, and thanks for letting me invade your club meeting tonight. And I guess it's probably dinner time in California, so I need to go make my wife happy.
I appreciate
you.
Thank you very much. By the way, my email's good on QRZ. I get a couple dozen emails overnight. I sit down and I answer every single one over 2 cups of dark roast Italian coffee. So if you have any questions or comments, you want to try to throw me some more puzzling questions, by all means do it. I'll do my best to respond the next morning.
Thank you very much.
Thank you.
Okay, thank you so much. I'll take off now, let you guys get to your own business. Good to see you, Becca. Thanks so much. Bye-bye now.
All right, bye.
Got it on the
Yeah.
bank across from the next station.
All right, so Sam is setting up. That looks like my polar duck tripod. Is that right?
Yeah, this is the one you linked on that version 2 that you put out.
Yeah.
And it's got the 2-foot aluminum piece there. I've got a little mirror mount
Yeah.
on here.
Yep. Yeah, that's the old version of the polar duck where they didn't have that telescoping tube on top. Now they do, but that's exactly the way I did it when I bought my old polar duck. I had to put an extension tube on top, but now they've got a telescoping tube built in.
Yeah, I'm just been like, I know there's some improvements, but this one does work, so I've just been
Oh no, it works. Yeah.
got the 70-foot whip, the linked radials with the bullets there. I actually had to cannibalize so I don't have it on this, but you can imagine there's the CB stud mount here and this
Yeah.
in there. So this is kind of how this would be configured.
Fantastic. And how do you elevate the radials?
I have there's a guy in our club, Jeffrey 85JT. He just he went to Lowe's and just picked up these $4 electric fence post mounts. These are working great.
Oh yeah. A lot of guys use those, and they also use the those bright orange snow markers, which were hard to find in California, so I had to go to Amazon. But they have them, and I ordered some of those. Pretty inexpensive. They work really well, very firm. They're bright orange, about 4 feet long. As long as you got it 4 feet long, elevated, you're all set. As long as they're non-conductive. I had a guy use tomato stakes with a steel core, and he kept telling me, he says, "How come my radials are so much shorter than yours?" And I said, "Because you're using steel core fiberglass stakes. Cut them open. You'll see it's got metal in the middle. They're counting as part of your radial. So as long as it's non-conductive, you're in good shape."